Hello and welcome to Computational Domain. My name is Adam, and in this tutorial I will show you how to solve ordinary differential equations using neural networks. The first example which I will go over is first-order ODE. A general expression of a first-order differential equation is given by this equation. I will define the domain of x from 0 to 1. Additionally, the boundary condition at x equals 0 is set to some constant a. The theory behind solving differential equations using neural nets is minimizing the loss function. Because minimizing the loss function is equivalent to solving the differential equation, it is possible to teach the neural nets to predict the solution of the equation. The output of the neural network will represent the solution y. The integral loss function will be defined using the mean squared error. The loss function is split into two parts. One is based on the differential equation and is referred to as MSEF. And the second one is based on the boundary conditions and is referred to as MSEU. So first we must define the neural network. This network will have one hidden layer, and the sigmoid function is used for the activation. Of course, this can be programmed using one line of code shown here in the comments. Of course, without the bias. But of course, it is good to practice the more formal way of coding the neural networks in PyTorch. So let's run these lines. The first example of ODE is defined as the following. So the ODE is simply y prime equals to e to the power of x. And because the boundary condition at x equals 0 is 1, the exact solution to this equation is y equals e to the power of x. First, let's define the function f and the loss function. Now we can run this cell and define the optimizer and train the neural network using the backpropagation. For the optimizer, I decided to use the LBFGS optimizer. I will not explain how this optimizer works. If you're interested, then you can read about it on your own. I will also share a link to the article in the description. If you want, you could also use a different optimizer, such as the Adam optimizer, which of course is a bit simpler, but then you should keep in mind that it requires more epochs, about 10,000. In this case, we can simply use 10. So let's train the model. Lastly, we can predict the full solution using the trained neural net and compare the predicted solution to the exact solution. So let's import the pyplot from matplotlib. Now we can compute y using the neural network and plot the results. As you can see, we managed to successfully predict the solution to the equation. Since it is a very simple case, the results are extremely precise. Another example which I would like to discuss is a second-order ODE. A general expression of a second-order differential equation is given by this equation. I define the domain of x ranging from 0 to 1. Additionally, the boundary conditions at x equals 0 and x equals 1 are set to some constants. In this case, it's a and b. So the functions of second-order ODE are defined as shown here. And the second-order differential equation becomes simply y double prime equals -1. And because the boundary conditions at x equals 0 and x equals 1 are set to 0, the exact solution is equal to y equals -1/2 x squared plus 1/2 x. The only difference between this case and the previous case is that there are two boundary conditions which must be included in the loss function as shown here. And of course, because we have two boundary conditions, we have to multiply it by 1/2. And of course, in the loss function, I also defined y double prime instead of y prime. And once again, it was possible to predict the solution using the neural networks. So that's all for this tutorial. Until the next episode, bye.